it is in fact a wave. And because it is an electromagnetic wave, it has a transverse mode of propagation. And because it has got transverse mode of a propagation, it propagates by formation of crests and troughs. So this will be the mode of propagation. So the higher points above the time axis or x-axis, the apex points are called crest, and below the time axis or x-axis, the bottommost points are called troughs. Okay, so this is how a light wave or an electromagnetic wave propagates. Then where is light used? It is used in photosynthesis, and also on the other day we were discussing that light is used for long distance communication. How light travels or how light is used for long distance communication. Light is used for long distance communication by means of optical fibers. Okay, and what are optical fibers? Optical fiber is itself a bundle of nano diameter, Okay, fibers, that means one bundle or one optical fiber cable will have a huge number of nano dia fibers. And when light or electromagnetic wave is incident through these optical fibers, those electromagnetic waves will undergo multiple internal reflection. They will undergo multiple internal reflection, and they travel long distances with almost no loss of energy. Okay, so light is used for long distance communication via optical fibers, though optical fibers have got multiple uses. It is used in, you know, those medical fields, surgeries, so those on to see the interior part of the body, those on. So it is also used for this. Okay, so electromagnetic waves have that property of traveling long distances through optical fibers. So like electromagnetic waves, other name or give an example of electromagnetic wave, it is light wave. All right. So what is the nature of light? Light has three natures. One is ray nature, another is a wave nature, and another is a particle nature. So how do we know that light has a ray nature? We know certain phenomena like reflection and refraction. So these phenomena we see. Based on that only we can guess that light has a ray nature. That means that a rectilinear propagation of light. Light travels in a straight line. And then light has a wave nature. All right, the wave nature of light was first proposed by Huygens. Okay, so we know certain phenomena like diffraction and interference. So as we move on in this chapter, we will definitely know about reflection and refraction. That's a part of syllabus. But what is a diffraction? Diffraction is if you have an obstacle and there is a source of light, and okay, and if light exits from this source, okay, so this obstacle is a hindrance in the path of light. So what exactly should happen is, if there is a screen here, we should have a bright zone here, and where this obstacle is, in this part of the screen, there should be a dark patch. But it never happens. If there is an obstacle, then also the complete screen will be bright. Okay, that means how is it that there is an obstacle on the way and light reach the complete screen? It's because that light has the habit of bending, B-E-N-D-I-N-G. Light has the habit of bending at the edges of obstacles. So light reaches the complete screen. Obstacle is something, a hindrance. All right, that means when you have a source of light, so this is that source of light, and you have an obstacle. Obstacle means something that it doesn't allow. That means you have a plate here or a cardboard here. So you have a cardboard here, say for example. So exactly what should happen if there is something of that kind? Then say for example, there is a screen on the other side. So what we should expect is this light rays will travel all the way like this, but here it is stopped. Here it is stopped and it travels all the way here. So it travels all the way here. So according to our imagination, light should be in this place and in this place. And light should not be where? Light should not be in this part. Okay, because in front there is an obstacle, but it never happens so. Why it never happens so? Why? Because light has a habit of bending, B-E-N-D-I-N-G, bending at the edges of obstacles. So light hits the corner and bends and reaches finally this zone. So as an example, we have obstacle once again, and there are refraction, which is direct topic of this chapter. We are about to learn about it. Then I said that light has a wave nature. Wave nature of light was first proposed by Huygens. Okay, Huygens. Okay, so the pronunciation Huygen. Okay, so this person is responsible for introducing wave nature of light. Okay, so how because certain phenomena like diffraction and interference are seen. Okay, so then this guess was done. Diffraction means a bending of a ray of light at the edges of an obstacle. Then what is interference? Interference means, so if you have a slit, say slit 1 and slit 2. So light being wave nature, light is a wave nature. So light travels by formation of crest and trough. Light travels by formation of a crest. So the white lines are crest, the blue lines are trough. Trough means, you know, that here crest is the upper part, like on a still water, you drop a pebble. Then those wave parts which come up, they are crest. Same amplitude wave part will be at the base from the surface. Those bottom parts, bottom maximum parts are called troughs. Okay, so light being wave nature, it travels or propagates by formation of crest and trough. Okay, so like this. So when it reaches the obstacle being a cardboard or an opaque object, it stops the light waves, but there are two slits, okay, through which light can escape. So through the two slits, light forwards or propagates in form of, that means through the slits light can escape. Okay, so whenever we are in a dark room, somewhere from the window or somewhere we see a speck of light like that. So like this the light propagates forward. And then if we have a screen here, so these crest and troughs reach here. Okay, now the regions where, so on the screen like this, you see here there is an intersection point. So like this is an intersection point. Okay, so like that, as this wave move forward like this, the wave move forward like this. Okay, so from the two slits, the waves move forward. So on the screen, when they reach the places where two crests intersect, that means slit 1's crest and slit 2's crest intersect, or slit 1's trough intersects with slit 2's trough. So those places will be bright patches. Okay, and the places where in between, the places where the crest of a first slit and trough of the next slit intersect, those places will be the dark patches. The orange is a dark, you take it like this, because screen is black in color. If I write black if I write with black pen, that may not be understood. So on this screen there will be alternate bright and dark patches or illuminations, you take like that. So on the screen, as the wave propagates or moves ahead, so the first slit crest, second slit crest may be intersecting somewhere on the screen, or the first slit trough and second slit trough that may be intersecting on the screen. So the places where two crest or two trough intersect, that place will be a bright place. And the place on the screen where the crest of slit 1 and the trough of slit 2 intersect, that will be called destructive interference. You know, where there is a bright patch, that is the constructive interference. Constructive interference. Constructive interference will give a bright patch on the screen. But places on the screen where the first slit's crest and second slit's trough intersect, that will be like the positive intensity and negative intensity plus minus 0. So finally 0 intensity. So that part on the screen will be a dark patch. So where on the screen, as this wave moves ahead, okay, on the screen, if the crest of one slit and trough of the other or vice versa intersect on the screen, that place will be dark patch, and that is called a destructive. That is called a destructive interference. All right, so what is constructive interference? Those interferences that lead to bright or illuminated patch on the screen. Destructive interference means that leads to dark patch on the screen. So this is what interference. And because diffraction interference, you know, reflection, refraction, diffraction or interference, these are not discovered things. They are actually existing things. People have observed it. All right. And after observing these phenomena in nature, they have given certain behaviors, or they have labeled light with certain behaviors. Okay. So light do behave like a wave. Light do behave like a ray. You got the point? Okay. And then light, the third nature, light has particle nature. That Albert Einstein proved this when Albert Einstein was given Nobel Prize for photoelectric effect, though he wanted photoelectric effect, though he wanted Nobel Prize for his, what theory, special theory of relativity. Special theory of relativity, general theory of relativity, everything was done by Einstein. But he was not given Nobel Prize for his theory of relativity. He was given Nobel Prize for photoelectric effect. Okay. So, so what the third nature of light is particle nature of light. So how do you, or how one came to know that light has particle nature? In fact, far before Albert Einstein, Isaac Newton gave this concept through the corpuscular theory of light. That means light travels in form of corpuscles. Corpuscles means tiny particles, and that 7 colors or whatever colors of light we are able to see, that is due to the size of particle. Okay, so those all we have in our syllabus, we'll discuss. So particle nature, light has particle nature of light. And how do we come to know? Because we see certain phenomena like photoelectric effect. What is photoelectric effect? Photoelectric effect is when photo means what? Other name of a light. Okay. So when photo falls on a photovoltaic cell, means what? Solar cell. When photo means a light falls on a solar cell, you know, the solar cell starts producing electric current. Okay. So photoelectric effect is how wave is related to diffraction. Excellent. Actually, no. If it is in form of a wave, then only it can bend. If light has just a ray nature, it should go by the edges of the obstacle straight. But because it has a wave nature, it has the ability to bend. Like when I tell you like this, it appears, you know, the moment say you have the obstacle and the light reached this point. So here, how is it propagating? It is propagating by formation of crest and trough and crest. You know, it advances. You have to understand, like when I draw like this, you won't understand, but in water waves, like in still water, you drop a pebble. And there, as the wave advances, You just take a cardboard and place it. And it doesn't mean that you placed a cardboard, the wave will not move ahead. In front of your cardboard itself, you will see the up crest part and the down trough part. That means you will see that the wave is still moving ahead. That means in front, you know, in the seas, oceans, huge, large ships. Okay, they are in fact obstacles to the wave, but because a ship is there, never a wave stopped coming the shore. Okay, again the philosophy may be different. The sea waves are due to the that winds, those all other things. But you can understand diffraction. Compare it with water waves. Okay, if you place an obstacle in a ripple tank, the ripples won't stop. Okay, so in that way, I hope to some extent I could explain this. Okay, so that means we have to compare wave nature. Acha, diffraction is what? Diffraction is a bending of a bending, bending of a ray of light at the edges of an obstacle. So this is the definition of a diffraction. That means light rays at the edge of, you know, early morning sometimes, or else outside room is bright and we are inside a dark room, just we open the door, we will see that light just tears up and comes inside, and at the door edge you will see a sector formation. Okay, so it happens. Why it happens? Because it has that property of a wave. Which wave? You compare this wave to a simple water wave, because water wave also propagates by formation of crest and trough. Okay, so that's what particle nature. So all right, so sometimes you don't understand, it's okay, I may be repeating those topics as we move forward. Okay, we are perfectly in the introduction part. So the third nature of light is light has particle nature. You know what? Light travels in form of ray, light travels in form of waves, light travels in form of particles also. That means it has got all of these properties. That is, light is something like a multidisciplinary kind of thing. How one came to know that light has particle nature? Because whenever light fall on solar cell, okay, solar cell, which is a semiconductor means what? Generally it is an insulator, but when light falls on it, it behaves like a mild conductor. On the periodic table, you see the carbon family, exclude carbon family. Next to carbon family, you have silicon, germanium, indium, those all. Okay, so those all are semiconductors. Okay, left side of a carbon family, you have all non-metals, which are insulators, and right side you have non-metals, which are insulators. So semiconductors, left side you have conductors, right side you have insulators. Between conductors and insulators, the carbon family members, excluding carbon, are semiconductors. Okay, so what I'm saying you is, when light falls on a semiconductor like silicon, light falls on a semiconductor like silicon or germanium, they are semiconductors. Silicon and germanium are the substances with which solar cells or photovoltaic cells are made up of. So when light falls on these are generally insulators, but if light falls, they behave like mild conductors. Okay, right now, you know, solar cells efficiency is at 25%. Generally, you know, a raw silicon chip or a raw germanium chip will have an efficiency of only 1%. But if these are doped with some other impurities, some other elements, they will show the efficiency of 25%. And this is the right now efficiency of semiconductors. When light falls on these kind of semiconductors, they become conductors. Okay, so that is called the photoelectric effect. Photoelectric effect means light energy is converted to electrical energy. How? When light energy falls on semiconductors. Okay, so this is how it is understood. So why does this happen? Light energy. Shakti, are you there? Are you listening, or I'm just talking myself? Are you there? Just you can raise hand sometimes. It's okay. Can you? You're listening what I'm saying, or I'm going much of theory? Okay, we'll fatafat, yeah, we'll fatafat come to the essence of the chapter. This is all quite basic things, okay, but just I felt we should discuss. So because light energy has the ability to get converted to electrical energy when it falls on photovoltaic cells, means like silicon, germanium or solar cells, then it was realized that light has particle nature. Means what? Light travels in form of particles, not exactly individual particles the way Newton said in Newton's corpuscular theory of light, but light travels in form of packets of particles, and each packet is known as a photon. Each packet of a light is called a photon, and every photon has an energy of E is equal to h nu. Okay, E is amount of energy each packet of light has, h is a Planck's constant, and nu is the frequency of light. Means one color light has got one frequency. Okay, so depending upon the color light, like violet light's wavelength is lowest, so its frequency is highest, right? So violet light's frequency, violet light's frequency is greatest among the visible light. So violet light's energy is more. That means on solar cells or photovoltaic cells, if a violet light or a blue light is incident, comparatively it will produce more electrical energy than when red light falls on it. Okay, so red light means, you know, that means energy generation in photovoltaic cell is not due to the heat energy of the sunlight. Understand? You understand? When solar cell means what? Put it in sun and you get electrical energy. That is not due to sun's heat energy. Okay, sunlight means generally we think that those infrared heat radiation. It's not that. Red light's wavelength is highest, so its frequency is lowest. So red light will have very less energy. So if red light is incident on solar cell, that's why solar cell, you just take it below your house, a tube light also, it works. Okay, so that's it. So light has particle nature. Light doesn't travel in form of individual particles. It travels in form of packets of particles. Each packet is called a photon. Every photon has an energy of E is equal to h nu. E is the amount of energy, h is the Planck's constant. This number I never try to remember, because whenever we solve numerical problems, Planck's constant, this number will be given. Okay, so much of the constants which are not in regular use for calculation is not remembered. Maybe somewhere when we cross the border of class 10th, people remember, but I don't know right now. So h is Planck's constant and nu is frequency of light. Okay, so photoelectric effect, that means photo generates electric effect. So photoelectric effect due to particle nature. So that's all the philosophy of nature of light. Okay, now we'll come to the main topic of the chapter. The main topic of the chapter is reflection of light. So we should know the definition of reflection. I just take up this slide. Okay, so how do we define reflection of light? This definition is a popular definition. Okay, so what is, or how we define reflection of light? Reflection of light is the phenomena of bouncing back of a ray of light when it is incident on a polished surface. Okay, so this is the definition of reflection of light. So till now what we have heard, we just saw what is light, basic things about what it is. Energy, it's a wave, how it travels, what it is used for, what are its nature. It travels like straight line, it travels in form of wave, it travels in form of particles also. And when it travels in form of a straight line, it does this. So what it does reflection. And what is the definition of reflection? Reflection is the phenomena. You see, reflection, refraction, diffraction, interference, those all are phenomena. Phenomena means what? If you send a ray of light on a polished surface, definitely it is going to bounce back into the same medium following certain rules and regulations. So every time what happens when you do this, those are called phenomenal. Okay, so it is a phenomena, right? So phenomena of a bouncing back of a ray of light into the same medium when it is incident on a polished surface. All right, so we are talking about polished surfaces. So assume that we have a polished surface, though I'm not using the word of a mirror, okay, because we'll go officially into the chapter. So this is that incident ray, right? So incident ray at the point of incidence. So the ray of light is incident on a polished surface. Okay, so this ray of light has to bounce back into the same medium. That phenomena is called a reflection. And if we go detail into this one word reflection, there are types of reflection. Diffused reflection, polished reflection. Polished reflection means when light is incident on a polished surface. Okay, that means in that case, what happens at the point of incidence, if I happen to draw normal, then angle of incidence is equal to angle of reflection. Okay, this is that. Another is called a diffused reflection. Diffused reflection is that what you see in cinema halls. In cinema halls, you will have, the screen is made up of cloth, obviously. And from the projector, the light rays are incident. Okay, from the projector, the light rays are incident and light rays hit the polished screen. Okay, and they will be reflected in a diverse direction. And these reflected light rays will reach every audience in the cinema hall. So every corner people who sit in the cinema hall, they can see what is going on the screen. But if cinema hall screen is a polished surface, then the projector is in front. So light rays will be reflected in the is equal to angle of reflection. Okay, that means when we have a polished surface, so though in my notes, I have not mentioned the types of reflection. Okay. So obviously, when ray of light is incident on a surface, there are no hard and fast rule that the surface will be polished surface. Every time now when I'm sitting in this room, light is incident on the 4 walls, ceiling and floor. And all the 6 surfaces are rough surfaces. And because everything is a rough surface, light is reflected in different directions. That's why I'm able to see the complete room. Otherwise, I won't be able to see. Those are simple things. Okay, so the first law of reflection. Okay, this is actually what is wanted examination point of view. So when a ray of light is incident on a polished surface, so this is the incident ray. At the point of incidence, if we happen to draw a normal, the ray of light is bounced back into the same medium. So this is the reflected ray. Okay. And then according to law of reflection, the angle of incidence is equal to angle of reflection. Okay. So at times, what is the angle of incidence? Angle of incidence is angle between incident ray and normal. Angle of reflection is angle between reflected ray, right? Yeah, spelling check, right? So, we can classify further spherical mirrors as concave mirror images. The characteristic features of images formed by plane mirrors and the spherical mirrors. For that purpose, we will use certain symbols. Okay, symbols like when I use the small letter U, I'm talking about, okay, what is the meaning of image distance? Image distance is a distance between my image in the mirror and the surface of a mirror. Then I'll use certain, when I stand in front of plane mirror, the distance between me and the mirror is always equal to the distance between my image and the mirror. Means what? For a plane mirror, object distance and image distance are always equal. First point. Next point, height of object is always equal to height of image. Okay, that no, when you stand in front of mirror, you and your image are of same size or same in every dimension. Okay. And then this is most important part, magnification produced by plane mirror. Magnification produced by plane mirror. Magnification produced by plane mirror is always a plus a 1. Okay. So sometimes we get questions like, what is the meaning of m is equal to plus 1? The meaning of m is equal to plus 1 is, this one number tells that hi, height of image, is equal to height of object. And this plus symbol always tells that if object is erect, image is also erect. If the object is upside down, image is also going to be upside down. So the plus symbol in the magnification tells that for plane mirror, how you will show the object, the image also will be exactly like that. Okay. And then what plane mirror does? It does lateral inversion. Plane mirror does lateral inversion. Plane mirror does lateral inversion. You understand? Well, I've just shown the letter, capital letter B, Bombay. Okay. So how it does lateral inversion. So these are basic characteristic feature of plane mirror. Okay. And something else, because this chapter deals with ray diagrams, how the image formations occur for plane mirror. Say for example, we have this polished surface, which is a plane mirror. Okay, and this is the base. Okay, and then this is the person who is in front of the plane mirror. How this person's image is formed in the mirror. Okay, for that, okay, so from this person, a ray of light which is incident normal to the plane mirror, it is reflected also in the same way, because I said no, laws of reflection. Angle of incidence is equal to angle of reflection. And what is angle of is incident on the plane mirror? Normal. Okay. Okay. So it is incident normal. So it is reflected also normal. Okay. And let us take, for any image formation, we need two rays. So if a ray of light is incident oblique, it is reflected also oblique. And in this process, what happens, this oblique ray appears to have started from somewhere. This normal, the ray of light from the object, means the person, okay, that it appears to have started from somewhere else. When it is instant normal, it appears that the reflected ray means, you see, this is object distance, and this will be the image distance. Okay, so like that. So it appears as if the person is inside. The person is inside the mirror. Okay, so this is how the plane mirror forms the image. So height of object is equal to height of image, but there will be only one lateral inversion. So this is how plane mirrors, form image. Okay, so that's it. So today what till now what we have learned is definition of reflection. I don't know, you must be knowing definition of reflection because we have learned somewhere in class 8th. Okay, and then the two laws of reflection, incident ray and reflected ray, are angle of incidence is equal to angle of reflection. Angle of incidence is equal to angle of reflection, and incident ray, reflected ray, and normal at point of incidence, lie in the same place. So two laws. Or convex mirror. Concave mirror and convex mirror are part of a hollow sphere. They are part of hollow sphere. So from this sphere, from its surface, if you just cut out a small section, okay, something like this, you cut out a small section, this is somewhere center of the sphere, and you know, you have cut out something like this. Okay, so this, you have taken out a portion, an area from the surface of the sphere. So this surface or the portion of the sphere or sphere, hollow sphere, if this hollow spheres outside. Outside is painted, and the inside, cave part is the polished surface. Okay, if outside painted and inside is inside is the reflecting surface, then uh, such a mirror is called a concave mirror. Such a mirror is called concave mirror. If inside is painted and outside bulging surface is the polished surface, means reflecting surface. Okay. So what is a concave mirror? Concave mirror is a part of hollow sphere whose outside part is painted and inside surface is the reflecting surface. And what is a convex mirror? What is a convex mirror? Convex mirror is a part of hollow sphere whose inside is painted. And if we can see it through a closer distance, our nose, obviously that part only will be visible in the spoon, that will be upside down. That is, concave mirror has that characteristic feature of magnifying things and turning it upside down also. Right, so that's how we define the spherical mirrors. Concave mirror is outside painted, inside reflecting. Convex mirror, inside painted, outside reflecting. And then what we should know about the spherical mirrors, we should know the parts, P-A-R-T-S, of the mirror, A-P-E-R-T-U-R-E. So aperture. What is aperture of the mirror? Aperture is the size or diameter. Aperture is the size or diameter of any mirror. That means when you cut out this mirror, it will be a circular, just like a bowl. It will be small sized, not much depth having bowl. Okay. So the diameter of, like this it will be. Okay. So the diameter is called aperture. Okay, diameter of the mirror is called aperture. Then the center of the mirror, where I'm writing P, center of the mirror. Okay, what is principal axis? Principal axis is an imaginary line joining the center of curvature and pole of the mirror. Principal axis. Okay, on the other day I was writing principle. Actually, it's not a principle. Principles are rules and regulation. This is principle, P-A-L, because this is the basis of all the ray diagrams or all the numerical problems we are going to do, sign conventions we are going to take. So it is that principle on which the complete philosophy of reflection and refraction of light depends upon. So it's a principal axis, and it is what? It is an imaginary line. Right now, it is an imaginary line connecting the centers of the two mirrors, but we will be handling individual mirrors. No. So then it is an imaginary line joining center of curvature and pole. Okay, so these are definitions I should write on the screen, but when I'm saying, you can keenly listen to me. And because since long duration, I am only one direction talking, I don't know how many things have gone into or how much you have understood, but you think today we have not discussed much. We have discussed what is light, what are the nature of light, how we come to know that ray nature is there, how we come to know that wave nature is there, what is photoelectric effect, means particle nature of light, understand? And then we of that circle is called pole. Okay, right. Now this sphere has a center. Okay, this sphere has a center. The center of this sphere, of which the two mirrors are a part, is called the radius of the hollow sphere of which the mirror is a part. If not like this, we can define a radius of curvature as the distance between pole of the mirror and center of curvature. Okay, radius of the hollow sphere of which the mirrors are a part If not, the distance between center of curvature and the pole of the mirror. Like this we can define center of curvature and radius of curvature. Center of curvature is a point of line joining pole and center of curvature is called principal focus. So what is principal focus? Principal focus is defined in two different ways. Principal focus is the midpoint of line joining center of curvature and pole of the mirror. That's one definition. There is one more definition. One more definition is, say for example, we have a mirror. Okay, it is a concave mirror. So what is principal focus? Principal focus is a point on principal axis where principal focus is a point on principal axis where the parallel beam of light rays after reflection converge to. That means after reflection, these light rays will pass through which point? That point is called principal focus. And that point exactly lies at the midpoint of the line joining center of curvature and pole. Okay. Last part of spherical mirrors is focal length. What is focal length? Focal length is the distance between principal focus and pole of the mirror. The way radius, the distance between focal length is the distance between principal focus and pole, right? So that's it. So these are various things. And then you see here, the radius of curvature is a distance between center of curvature and pole. Focal length is a distance between principal focus and pole. And where is principal focus? Principal focus is a half the distance between center of curvature and pole. Okay, that means what? F plus F. If principal focus is a midpoint of C and P, okay, and focal length is a distance between principal focus and pole. Okay, so this is right. If this is midpoint, this distance and this distance are equal. Okay, distance between F and P, that is called focal length. So this distance and this distance are equal. So this is also F. So F plus F should be R. Okay, so F plus F should be R. So twice F is R. So twice the focal length is the radius of curvature. Twice the focal length is the radius of curvature. So today what we have learned till now is up to the parts of a mirror. That's all. Mirror has only these parts. 1, aperture. 2, pole, which is center of the mirror. 3, center of curvature, which is the center of the hollow sphere of which the mirrors are a part. Center of curvature is okay. That's of course that one. Then radius of curvature is distance between center of curvature and the pole, or the radius of the sphere of which the mirrors are a part. Radius of curvature definition is that. And then principal focus. Principal focus is perfectly the midpoint of line joining C and P, center of curvature and pole. Distance between principal focus and pole is called focal length. If principal focus is at the midpoint, then radius of curvature will be at double the distance of focal length. All right, so this is parts of mirror and relation between radius of curvature and focal length. So we'll go for some